Hello, friends. Welcome to the world of quantitative techniques. Today, the concept that we are going to discuss today is the most easy and the most known part, that is matrices. Let's understand first of all what exactly is a matrix. So, a matrix is a set or a group of numbers arranged in a square or a rectangular array enclosed by two brackets. So, as you can see, this has a kind of a rectangular, and this is a square also. This is also, we can also have 3 cross 3 types, also 3 rows and 3 columns also. So, we can have bigger squares also. So when we say a matrix, it means arranging. So if I take an example, let if supposing you go to a market, you have some daily purchases, you want to identify that what kind of purchases are we doing, or what is the purchasing capacity that we have, or what are the quantity of products we have been purchasing on daily basis. We can write in the rows and we can write in the column the number of days that we are having. So the entries that we are going to have, whether it's in the when it can be rectangle or it can be square, that means the rows or the columns can be equal or they may not be equal. If I have a structure like this, because we have a bracket being formed, so this is called as a matrix representation. Now, what is an advantage to this? Minimum advantage. First of all, it reduces the complexity or the complicated systems into simple expressions. As we can easily see, a grid formation is there. Also, a systematic, it is actually helping for go for a systematic method for mathematical treatments, and it is the most suitable part for computer programming also. So this has a huge application, whether it's a business management or whether it's going to be an IT professional. So, what are the properties? As we have said, that rows or the columns or the pattern that we follow. So, one is the row, second is the column. It describes the matrix. Now, first of all, we also write in the capital one, the A or B, etc. And we have I, comma J. I refers to the row and J refers to the column. So if I have a 3 cross 3 matrix, it means it is going to have 3 rows and 3 columns. If I have a 2 cross 4 matrix, the first one is referring the row and second is referring to the column, right? And the number, it is also called as the size of the matrix. And the elements will be your individual entries, will be called as the elements of the matrix. Okay. So this is the common notation, and I just discussed we are representing with the bold capital letter, and the elements or the entrants are called as the lowercase. So if I read this one, A11, A11 means the position of this element is first row and first column. Got it? If I say Aij, so Ij means it is placed on the ith row and the jth column. Got it? This is how we represent the matrices. There are multiple types of matrices, and matrices is one of my favorite topics also. So let's start with the column matrix or a vector. It is basically, it means that we have many number of rows are there, but the column is always one, right? So as you can see, we have multiple rows available, but there is only one column. So it the representation will be something like I cross 1. As we have read, I refers to row, J refers to column. So only one specific column is there. The rest are going to be the number of rows. So if I take this example, this has 3 entries in the rows. So this is 3 cross 1. This will be 2 cross 1. Okay? Make sense to all? Fine. Just like a column matrix, we have a row matrix. So just like column matrix, we have single row in this one, but we can have any number of columns. So the representation will be 1 cross J, right? One row and as many number of columns as we want. So if I read this, this will be 1 cross 3, this will be 1 cross 4, this will be 1 cross n. And as it is easy, 1 cross n means it is on the position first row and the nth column, right? Okay. Then we have the types of matrices. The first one is called as rectangular matrix. We all know that rectangle, the length is not equal to breadth. So similarly, when in this one the number of rows is not equal to the number of columns, that is called as a rectangular matrix. So if I have I and J formation, then I is not equal to J. If I have an M cross N formation, so we say M is not equal to N, where M refers to the number of rows and N refers to the number of columns. So you can see how many rows are there: 1, 2, 3, and 4. So 4 cross 2 columns are there and they are not equal. And here we have 2 rows and 4 columns. Clearly they are not going to be equal. This is an example of rectangular matrix. Fine? Okay. The next one is a square matrix. We all are well aware square matrix means that the length is equal to breadth. So the number of rows is equal to the number of columns, right? So we can say it is simply of order m, because if I say this is of order 2 cross 2, 2 rows, 2 column, we do not have an m cross n. N is same as m, so it can be also called it is of order 2. This one, if I say it has 3 rows and 3 columns, these are 3 rows and these are 3 columns, so it is of order 3, right? And we can have like 1 cross 1 is also possible. If I have a single number like this, single entry like this is of order 1 cross 1. So we can have as many number of orders that we want, and obviously a principal or the main diagonal. If you see this one, this is A11 and this is A22. So that means the place where I is equal to J, that particular line, these entries are called as your principal or the main diagonal. Okay. Now, what exactly is a diagonal matrix? The one we have learned earlier is a principal diagonal. That means only the entries where I equal to j is there. But when I talk about the matrix as a whole, in this one, first of all, it is a kind of a square matrix. Second, it has all the entries as zero except on the main diagonal. Okay? So that means if I have I equal to j, some number will be there. Now, this number can be 0, it can be 1, it can be positive, it can be negative, it can be fraction, it can be decimal, anything, but something will be there, right? But the rest of the portion where I is not equal to j, it has to be equal to 0 for all I and j. This represents for all. Okay? So, for example, if I check this place, this is first row and third column. This is 1 cross 3. Now, 1 is not equal to 3, so the element has to be equal to 0 over here. If I take this one, this is third row and second column. This is A 3 2. 3 is not equal to 2, so the position is 3 2, but the element has to be 0 over here. That is the condition of diagonal matrix. Now, there are specific types of diagonal matrix, and the most commonly used is your identity matrix. In this diagonal matrix, so when I say diagonal, पहली condition तो क्या हो गई? That it has to have all entries where I is not equal to j, it is equal to 0. Right? तो जो बाहर का ये है, it has to be all 0, right? But for I equal to j, the value has to be equal to 1, right? The aij has to be equal to 1. This is your unit or the identity matrix. So if I take this position, this is a11, this is a22, this is a33, this is a44. So all the entries are equal to 1 over here. This one is an order 2 matrix, 2 cross 2. If you can see, this is also equal to 1. So this entry has to be equal to 1. That is a specific kind of a diagonal matrix, right? Okay. And the most easy, the most comfortable is your zero matrix. And although it is very useful, it is really useful for all of us when we have linear equations being solved. So in this particular case, all the elements are going to be zero. So all aij, J कुछ भी हो, equal हो, not equal to any entry, this is going to be equal to 0. Next is triangular matrix. Triangular matrix is a specific kind of a square matrix. When I say square matrix, it means whose elements above or below the main diagonal are going to be 0, right? So this is my principal diagonal. So I can have all the entries above or all the entries below. They are your called as your triangular matrix. So as the name suggests, it is called as upper or the lower triangular. If we have the entries above or we have the entries below, they are called as the upper or the lower triangular matrix. As we can see, in which if we have entries above the diagonals, if are there, right, then that is called as upper triangular. Lower triangular में नीचे होगा, तो याद रखना, it is like, आप ऐसे समझ लो, for the upper triangular matrix the elements below are equal to 0 and we have numbers above them, right? If you can see, this is the principal diagonal. The below numbers are 0, but the above numbers, we do have above numbers. Now these again can be positive, negative, fraction, decimal, anything, 0, 1, anything can be there. But for this particular condition, this particular restriction, it has to be 0. Then we have the lower triangular matrix. The lower triangular matrix says it's a square matrix whose elements above the main diagonal are 0. So when I have this kind of a matrix, first of all, it's a square one. So all the entries above are going to be 0 and we are going to have entries in the lower formation, right? So this is called as a lower triangular matrix, and that is what we define, aij equal to 0 for I less than j. Then the next kind of a matrix is your scalar matrix, right? So it is a diagonal matrix, first of all. So as the diagonal says, it is going to be a square matrix. Now, whose main diagonal elements are equal to some scalar number, any constant number. Again, it can be positive, negative, anything, but all the numbers have to be same. As you can see, we have aij throughout, it's going to be same over here. It can be 111, it can be 668, it can be 777. So if you remember, we also have learned about unit matrix. So unit matrix is a special kind of scalar matrix. Unit is a special kind of scalar matrix. Okay, it's a special kind of scalar matrix. Please ignore my writing. All right. Okay. So I hope that you all are clear with the types of the matrices that we have. We have learned about rectangle, we have talked about square, we talked about row, column, unit matrix, square, scalar matrix, diagonal matrix, upper triangular, lower triangular, and all types, right? So now let's talk about the operations. Okay. So the first operation that we are understanding is called as the equality of matrices. Now, the two matrices are said to be equal only when the corresponding elements are equal, all the corresponding elements, which means if I have a matrix, let's say order I cross j, and one of the matrices, let's say m cross n. The rowth common row has to be equal to the corresponding row, and the column has to be equal to the corresponding column. Okay, so the dimensions are also equal. If I say this, if I read this, so this is a matrix A, this is a matrix B. Now this A11 and this B11 is same. This A12 is going to be same with B12. So if I have two matrix A and B, then Aij will be equal to Bij for all I comma j, right? Only then they will be called as the equal matrices. Fine, right? So if and only if A is equal to B, then we say that B is equal to A. And if A equal to B and B equal to C, then obviously A is equal to C, that we have for all the three matrices. Fine. The next one is your addition or the subtraction of matrices. Addition, that is the sum. Difference, that is the subtraction. So when I say addition, it means we are actually adding two corresponding elements of the matrices. For matrix A and matrix B, for example, if I have A11, we are going to only add B11 to get C11. Okay? So Cij will be equal to Aij plus Bij. And always remember that matrices of different sizes cannot be added or subtracted. 2 cross 2 matrix cannot be added to 3 cross 3, or 2 cross 1 cannot be added to 1 cross 2, etc. So the order has to be same and the corresponding entries element has to be added accordingly, right? So I'll just take an example in the previous slide only. If I have, let's say, A is, let's say, simple 1, 2, 3, 4, and I have B equal to 5, 6, 7, 8. And if I say A plus B equal to C, then C will be 1 plus 5, that is 6, 2 plus 6, that is 8, 3 plus 7, that is 10, and 4 plus 8 equal to 12. Right? So this means that we are actually adding the corresponding entries to each other only. And this is possible for only the same dimensional matrix. Right? This is not going to be for the different ones. So the order has to be clear. Order means the rows and the column dimensions has to be same. Right? Now, there are certain laws associated with the operations. We are also going to learn about matrix multiplication. So, first, let's complete the addition and subtraction. The first commutative law says that A plus B is equal to B plus A, right? And the associative law says that if I take B plus C first, and then add A, this will be same as A plus B and adding C later, right? So that is going to give me A plus B plus C. As you can see, for a rectangle matrix also we can have addition. So 7 is added to 1 to get 8, 3 is added to 5 to get 8, and so on, as it is clearly visible that we are adding only the corresponding entries, right? So let's just discuss about the commutative law. If I have A equal to 1, 2, 3, 4, B is equal to, let's say, identity matrix. So if I add B plus A and A plus B, then this will be 2, 2, 3, and 5, right? And if I add B plus A, B first and then A, so it is 1, 0, 0, 1 plus 1, 2, 3, 4. This is going to be equal to 2, 2, 3, and 5. They are same. So this proves the commutative law. And I hope that on the similar patterns you can try for the associative law, right? Okay. Now, a rule says if I add a null matrix either from the left hand side or from the right hand side, the output is going to be the same matrix. This is very easy to prove. I have A11, A12, A21, A22, and if I add 0 matrix, obviously the dimension has to be same, then this will be A11, A12, right? A21 and A22. Got it? So even if I add from, because 0 if I add to from any side, we are going to get the same results, right? Now, when I say a negative, right, or a minus a means we are having multiplication of all the elements with minus sign, right? When I have this minus sign, the output is going to be equal to 0. What does this mean? If I have 1, 2, 3, 4, and if I multiply all the entries with minus 1, so it will come minus 1, minus 2, minus 3, minus 4, the output will be 1 plus minus 1 will be 0, 2 plus minus 2 will be 0, 3 plus minus 3 will be 0, and 4 plus minus 4 is going to be equal to 0. Right? Or we can write something if I have to find the subtraction in general. So you can see this is an example of the subtraction in general. But if I have for the particularly for minus a, the output is going to be 0. Right? Okay. Now what exactly is a scalar multiplication? The matrices can be multiplied by a scalar. Now this can be a constant number, a single number, and when I multiply with this one, it means I am multiplying every entry with that particular number. Okay, so just we had as minus 1 multiplied with everyone. Similarly, we can have for any number. Let's say I have a as 3 minus 1, 2, 1, and so on, and k is 4. It means I'm multiplying each and every entry with 4. So what will be 4 times a? This will be 12 minus 4, 8, 4, 8 minus 12, 16, 4, and so on. Right? Again, if we multiply from left or from right, we are going to get the same results. The properties are quite easy. If I have A and B as two separate matrices, and if I multiply the sum with the scalar, that means we are also having the individual multiplication with both. So let's say a simple example. I have A, I'm taking a very basic, the identity matrix, and let me take B as 1, 2, 3, 4. Now, if I take, let's say, 2A, and I'm having with the same one 2B, then this will be 2002 plus 2468. Then we are going to get 44610. If I have A plus B, then this will be 1 plus 1 will be 2, 2, 3, and 5. If I multiply 2 with A plus B, this will be 4, 4, 6, and 10. So as you can see, the results are same, right? So this is the first property that we have proven. If I have k plus g equal to k plus a, right? So k plus g multiplied with a equal to ka and ga. So if we have two scalars being added, so let's say my k is equal to 2 and my g is equal to 4, then k plus g will be equal to what? 6, right? K plus g will be my 6 value. So that means we are multiplying 6 with the corresponding matrix every element, right? And we can also say that if I add 2 times matrix A and 4 times matrix A and then add it, it is going to give me the same result. Okay. Now, k times AB will be KA multiplied with B equal to A into KB. This we will be learning once we learn, you'll be able to understand better once we understand the multiplication. And similarly, we have this one. We can first multiply with first constant and then multiply with the second constant. Both are equal, right? Okay. So, next comes the multiplication of matrices. Multiplication of matrices means the product of two matrices. And the product of two matrices is also going to be another matrix. Right? Then we say the two matrices are multiplicable only if they are conformable. Conformable means the number of column of A must be equal to the number of row of B. Okay, which means if A is of the matrix M cross N and B is of the matrix P cross Q, then the number of column of A must be equal to the number of rows of B. That means multiplication is only possible when N is equal to P. If this is true, then the two matrices are called as conformable. Okay. Now, when I say conformable, it means we are trying to identify the rows and the columns, and the definition is clear. And it is, you can see, if I say A cross B equal to 7, अगर A cross B अपने को multiply करना है, let's say we have to find, and A is 1 cross 3 and B is 3 cross 1. So as you can see that both the rows and the columns of B and A are respectively same. So that means the matrix output will be of order 1 cross 1. So आप देख सकते हो जो इसका output आएगा that will be of order M cross Q. Okay. So the first thing that we have to keep in mind is your conformability. Okay. And the second one is your output will be in the form of M cross Q. Okay. Let's say this example. Now, if I have a matrix, okay, if I have a matrix of order 2 cross 1 and then second is 4 cross 2. Now, this 1 is not equal to 4, so it is not possible. Similarly, this 2 is not equal to 6, this is not possible. But if I have something like this is conformable and the output is going to be 2 cross 3. Let me take one more example. If I have a matrix 1 cross 4 and second is, let's say, 4 cross 3, then the output will be of the form 1 cross 3, because we are going to have in the form M cross B. Right? Okay. So how to multiply? Now multiplication is quite easy. Now what exactly is multiplication we are going to do? If you can check, the first matrix if is of order 2 cross 3, and the second one is of order 3 cross 2. Okay. Now, this is of order 2 cross 3. This is of order 3 cross 2. Conformability check done. Output will be of the form 2 cross 2. Multiplication अपने को करना है. Multiply is what? Multiply first A11 with the corresponding B1. Okay. Then add the next entry A12 with B21. Okay. And then add A13 with B31. So what we are going to do is, we are going to start with the first row of the first matrix, cover the first column of the first matrix. Once all the entries of the first column are done, we switch to the next one. Okay. So this is the pattern that we are going to follow. So we are done with B1. Now 1 1, then we are going to go for the B12. So what we are going to have is A11 with B12, A12 with B22, A13 with B33. Okay, so this, the conformability has to be there for all the entries, right? So we have all the entries, and you can see this will fetch you for A11, and the entries will be obtained as A11 with B11, A12 with B21, and so on. If I proceed with A11 with B12, A12 with B22, etc., the corresponding entries will be C11 and C12. Once we are done with the first row, we switch to the second row. So second row is starting from A21. So we have A21 cross B11 plus A22, second entry with the second one, third one with the third one. We are done with the second part, then we'll switch to the second column. So we have A21 with B12, A22 with B22, A23 with B32. Okay, so let's do this example. 1 multiplied with 4 plus the second entry is 2 cross 6, third entry is 3 cross 5. So my first C11 will be 4 plus 12 plus 15, 4 plus 12 plus 15, which is equal to 31. So the first entry C11 will be 31. The second one will be 1 will be multiplied with 8, 2 will be multiplied with 2, plus the third entry 3 will be multiplied with 3. So we have 8 plus 16 plus 9, that is 25 plus 8, right? Sorry, this will be 4. I apologize. 8 plus 4 plus 9, that is 12 plus 9, that will be equal to 21. Thank you, and rectify the error here and there. Similarly, if I proceed for the third one, then we have 14 plus 12, 4 into 4, that's 16. 16, is my audio available? 4 into 4, that is 16. 16 plus 12 plus 35, we are going to get 63, and so on. Also remember that I cross A will be equal to A. So if I have a multiplication rule, then the output is going to be same. Let's check this. So we have 1 cross 31 plus 0 cross 63. Second entry will be 1 cross 21 plus 0 cross 57. Second will be 0 cross 31 plus 1 cross 63. Similarly, we have 0 cross 21 plus 1 cross 57. So the output is 31, 21, 63 and 57. Okay. As we have some operational rules for addition, we also have some operational rules for matrix multiplication. As we know that conformability is the key rule we have to keep in mind whenever we have the matrix multiplication. But there are certain rules, another, which you can get after solving some data. First is multiplication of a matrix with the corresponding order identity matrix is going to give me the same matrix. Okay? Which means if I have a matrix of order 2 cross 2, and if I multiply identity 2 cross 2 also, then the output will be the same matrix same. Or as it says, now this result is also possible if I have a matrix, let's say 2 cross 3, right? Now if I have a matrix of order 2 cross 3, because this can come into your minds, ma'am, what will happen if I have a rectangle matrix? So if I have an order of 3 cross 3, right, conformability check, then the order will be of order 2 cross 3. So whether it is a square matrix, whether it's a kind of a rectangle matrix, in any of the matrices is possible. But again, but you have to check for the conformability. That means that the identity matrix has to be of the same order as that of the column of the first matrix. Okay. Just like associative law in addition, we have associative law in multiplication. That is, A times BC is equal to AB times C, which is equal to ABC. Distributive law from the left or the right, they are called as the first distributive and the second distributive. If I have B plus C and if I multiply with A, the result will be AB plus AC. Similarly, if I add A plus B earlier and multiply C, then that will be AC plus BC. This is the second distributive. Also, AB may not be equal to BA always, because BA may not be conformable. The simplest example is, let's say I have 1 cross 3 and I have 3 cross 1. Okay. So if I multiply with these two matrices, now A cross B will fetch me 1 cross 1 as the matrix C, right? But if I multiply BA, that means I am multiplying 3 cross 1 with a matrix of 1 cross 3. Again, conformability possible, but the output will be of 3 cross 3, right? So this matrix is clearly not going to be equal. So AB may not be equal to BA in general, as they may not be, they are going to fetch it. And obviously, it is not going to be always true that they are going to be conformable. Supposing if I have a matrix like 2 cross 5 multiplied with 5 cross 1, so result will be clearly 2 cross 1. But if I reverse the positions, that means I'm having 5 cross 1 multiplied with 2 cross 5. Obviously this is not conformable, so multiplication is not at all possible here, right? Also, if AB is equal to 0, neither A nor B necessarily be equal to 0. It is not compulsory that we are multiplying the two matrices which are having all the elements as 0, going to give the fetch you a 0 matrix. It is not going to be always true. Also, if AB is equal to AC, then B may not be equal to C. That means the cancellation law may not work for matrix multiplication. This is possible only when we have the identity matrix. But for general matrices, this is not going to be true throughout. Okay? Okay. So as the examples are there, it's very easily there. We have a matrix of 2 cross 2. Obviously, you can see the two matrices S multiplied with T and T multiplied with S are fetching me two different answers. So they may not be equal. Similarly, if I say that A into B is equal to 0, neither A nor B may be equal will be equal to 0. If I say this, If I multiply these two matrices, we are multiplying 2 cross 1. The second is plus 1 multiplied with minus 2. Second entry is 1 cross 3 plus 1 multiplied with minus 3. Similarly, 0 comma 2 plus 0 multiplied with minus 2. Then we have 0 multiplied by 3 plus 0 multiplied with minus 3. Right? So what we are getting? This is 2 minus 2, 3 minus 3, 0 and 0. The output is 0, 0, but neither A nor B is 0 matrix. Okay? And the next one, the next matrix operation is the transpose. Transpose means shifting 180 degree. That means in simple terms, the row become column and column become row. Okay. So if I have a matrix of order 2 cross 3, when I apply the transpose, it becomes 3 cross 2. So I write it as that aij is a matrix, and if I take the transpose, the roles reverse. So it becomes AJI, right? If you just see here, we have a matrix 2, 4, 3. This is my first row. This is my second row. When I take the transpose, it becomes my first column and my second column respectively. Right? Okay. Also, this means that we are going to reverse the dimensions of the matrix A. Right? I hope it's clear. Some properties of transpose matrix. If I add two matrices and take the transpose, it means we are taking separate transpose and then addition. It means the same thing. If I multiply two matrices and then take the transpose, it means we are taking the reverse of the multiplicated transposes, right? Because of the conformability, this rule happens. Then, if I have a scalar and I multiply with a matrix A and then take a transpose, it means the scalar can be kept out and we have the matrix transpose being there. And the transpose of the transpose is the matrix same. For example, if I have 5, 6, 7, 8, if I take the transpose, it will be 5. What? It will shift here. So we have the first row 5, 6, 7, 8. If I again take the transpose, right? So it will again get back to me to the same position, that is 5, 6, 7, 8. Right? Okay. So the examples are well clearly given to you in the video. If I take A plus B transpose, it is equal to A transpose plus B transpose. So we have A plus B, right? If I take the transpose, we get this result. If the transpose is here and then take it, the output is same. Okay, good. Now, AB whole transpose will be equal to B transpose, A transpose. Now, this you can see, this is my matrix A of order 2 cross 3. This is my matrix B of order 3 cross 1. Conformability level check. The output will be of order 2 cross 1, right? Multiplication now we are very clear. 1 with 1, 1 with 1, 0 with 2. This will be at the first entry. Second will be 0, 1, 2, 1, 3 multiplied by 2. That will give me the second entry. If I take the transpose of this, then the output will be 2, 8. Okay. And if I take B transpose and A transpose, let's say that the matrix here A is 1, 1, 0, 0, 2, 3. So the transpose will be what? 1, 0, 1, 2 and 0, 3, right? The matrix here is B is 1, 1, 2. If I take the transpose, it will be 1, 1, 2. Yeah, fair enough. Now, this is what? B transpose. This is what? A transpose. So, the output will be the same as you can see. Okay. Moving further, we have symmetric matrices. So, the symmetric matrix is a special kind of a square matrix that is symmetric if it's equal to its own transpose. Supposing it happens that the matrix, it is not always true, but it's a special kind. It happens that we have a matrix A and by chance it is equal to its own transpose, then that matrix is called as a symmetric matrix. And the key area you can see is that these two entries are going to be same. Only then we say it is going to be symmetric matrix. Okay? And when the original matrix is square, transposition does not affect the elements of the diagonal. Okay? And obviously identity matrix, diagonal matrix, scalar matrix, since their principal diagonals are there and all the entries are zero, so they remain unaffected. So I hope that you all are well clear with the concepts that we have discussed, and this basics of matrices is clear to all of you. So happy learning from us.